This problem is a mechanism problem, and where it's told that when you treat butadiene with HBr at 40 degrees, you get the product on the right. If you also use HBr in presence of peroxide at 40 degrees, you get the same product, albeit two different mechanisms. And it's asking you for the mechanisms to get to each one. Now, so your goal for the first case is to get to this product right here. So it's a Markovnikov addition. So you protonate to form the most stable carbocation you can. In this case, you're going to protonate to form this carbocation. Now, this carbocation is not just secondary. This carbocation is resonance stabilized. And so these two molecules are resonance structures of each other. These two molecules are the same molecule. They're just resonance structures of each other. The actual molecule looks something like that, where the electrons are distributed amongst those three atoms, with probably the largest delta plus there and the smallest delta plus there. Largest delta plus is here because this secondary carbocation is typically considered to be better than a primary, making this the major resonance structure. But the minor is still present. And the bromide can add to either one. So if it adds to this one, you get this product. And if it adds to this one, you get this product. And that's the product that the question is trying to get to. Now, for the peroxide one, the peroxide mechanism starts out with an initiation step where the peroxide splits into two. And the resulting O radical steals an H from the HBr. And that generates a bromine radical. And the bromine radical likes to add to the less substituted side to give the most stable radical it can. And like the carbocation, this radical is also resonance stabilized. And either of these two radicals can take an H from HBr. Okay. Now, this is a mechanism question where I gave you the product and you had to draw a mechanism to the target product. In this case, the product was this. So that's what you had to draw a mechanism to. You didn't necessarily have to draw a mechanism to this one here. Now, if I did this as a predict the product type question, the answer that I would expect would be to have both of these, regardless if you use HBr or HBr with peroxides. I'd expect you to write both of those because both of those are possibilities. And you would have to actually run the experiment to figure out which one was actually the major one. Now, a lot of people are wondering, why is this one the major one when the secondary carbocation is the better one? Okay. So now I meant to talk about this a little bit later on in class, but let's just talk about it now. You do this reaction at 40 degrees. The major product is indeed this. When you do this reaction at a much lower temperature, say minus 20 degrees, the major product is this. That's because this happens to be the thermodynamic product, and this happens to be the kinetic product. And what the temperature difference is has to do with equilibration. There is a barrier to going backwards. In this case, the barrier would be the last step. If you have enough energy to surpass that barrier, in this case 40 degrees or so, then the reaction can go backwards. So let's talk about this in terms of a way to think about it. First of all, thermodynamic product means it's the more stable product. Why is that product more stable? Well, for one thing, you can take a look at the alkene. That is a di-substituted alkene. This is a mono-substituted alkene. Di-substituted alkenes are more stable than mono-substituted alkenes, making that the more stable product, making that the thermodynamic product. Now, the kinetic product, that's the one that is formed the fastest. So when you treat it with HBr, you get this carbocation that's resonance stabilized. The actual molecule is a weighted average of these. And since secondary carbocations are better than primary carbocations, this is the major resonance structure, meaning this has a much bigger delta positive than this does. Since this has a much bigger delta positive, that makes it more attractive for the bromide to add to that. lowering the barrier of that reaction. So if we were to think about it in terms of an energy diagram, we would have the alkene, and we'd protonate the alkene. So the alkene would go here, have that activation barrier to get to the carbocation. Now here is where they start to differ. The more stable one is this one, based off of Zaitsev's rule. The less stable one is this one. So because it's easier for the bromide to add to the major resin structure because it's a higher delta positive at that position, we make the activation barrier for that one to be lower. And I really should make this first activation barrier to be the highest one, because forming that carbocation is the fast steps. The other steps are the slow step. Okay. So at low temperatures, the reaction doesn't go backwards. And so this is the major product. When you go higher temperatures, the reaction becomes reversible. Since it's a reversible reaction, then the most important one is the largest barrier going backwards, because that's the least likely one to happen, and that'd be the thermodynamic product. So the reaction may go over the smaller hump, but that's also the first reaction to go backwards. And you get just this slow accumulation of this product. So this is the major product at higher temperatures. Because of the reversibility. This is what's called the thermodynamic product. Now, I want to emphasize, I do not expect you to memorize which ones is the thermodynamic conditions, which ones are the kinetic conditions, because that's going to be different for each reaction. And a lot of it is literally just trying out the reaction and seeing what you get and then adjusting it afterwards. Okay? So, for this one, I would, if it was a predict the product type question, I would expect you to write for these products. I'd expect you to write for HBr and for just HBr, I'd expect you to write these two products. If it was HBr and peroxide, I would expect you to write these two products if it was a predictive product question. So on and so forth. Okay.